Our alpha substitution chapter has a couple of different types of enol, enolate, so carbon nucleophiles that we've studied. This is an enamine, which is also a carbon nucleophile in the same genre. We're just looking at a vinyl amine, and basically we have a masked ketone or aldehyde, as you already know about imines. So this is very similar to imines. We've made imines before using nitrogen and an amine compound and a ketone or aldehyde. So in this case we have an aminium salt that forms because there's two R groups on that nitrogen. So here's our aminium salt. That reaction continues on, and we actually lose a proton from the alpha position to get our enamine. So here we've got our enamine. And you can see that there's a resonance structure with that, where we have a carbon nucleophile right out here. So we're going to react that with some electrophile, and then we can alkylate that enolate. So enamines are masked ketone or aldehyde, and they are intermediate in reactivity between enol and enolate. So they're a bit milder than an enolate. Enamine. So reactivity is increasing as we go down. Okay, so we can get that enamine by interacting our ketone. We'll just take this ketone and let's do this mechanism of how we get that. First of all, the nitrogen, I'm going to use this 5-membered ring, 1, 2, 3, 4, 5, amine. So this is a secondary amine, and that's the key part of this, secondary amine. So that will, in the presence of maybe a slightly acidified condition, right? We said pH about 4.5. That nitrogen will attack and displace one of the bonds. So we'll get the OH and a nitrogen, and then our 5-membered ring, 6-membered ring down here where we started with, and there's still an H on that nitrogen. So I can lose that H. I can also transfer it internally, like so. And then I'll have the water molecule here that is now an oxygen with a plus charge. And that's a good leaving group. So what we can see here is these electrons right here can swing in, and the leaving group can leave, and we'll be left with our aminium salt. So then that aminium salt, it cannot lose a proton from the nitrogen, which is what we do when we have an imine that forms, because this has 2 R groups on that nitrogen, no more hydrogens to give. And so what happens next is perhaps it's the water that was lost even that can take a proton, and then those electrons will swing in here, and we'll be left with our ene, because once those move in, these will move out to the nitrogen, and so we'll be returning those lone pairs to the nitrogen, and we get our enamine. So that plus our H3O plus, little bit of acid present. So since it's less reactive than an enolate. Reactive, less reactive than enolate. It's a bit milder, so that makes it able to avoid side reactions. So let's look at the next page. We can use this enolate to do some alkylations with. So we can substitute with both alkyl groups and acyl groups. So here are a couple of examples of alkylation or acylation of an enamine. Our first example will be this enamine with an allylic bromide. And so I can see these electrons coming down here, and then this pair of electrons in the pi bond reaching out to attack in an SN2 fashion that allobromide. And so we'll end up getting the attached 1, 2, 3 carbons, 1, 2, 3. The new bond is right here, and then our nitrogen will have a double bond to it, and it will be an iminium salt. And we can work that up with H3O plus and return to the keto form. So we've done an alpha substitution with an enamine. In this case, we have a six-membered ring with our nitrogen. The key part is 2 R groups, and oftentimes a ring structure is used. And so we're going to bring those electrons down, and then the double bond, pi bond, will reach out and attack our acid chloride. Electrons swing out, they swing back, and then what we'll have is a new bond to that carbonyl because this leaving group left. So we have our new bond right here, and the chloride has departed. That will be our intermediary. So that's a 6-membered ring. So I will more accurately represent that with a plus charge, and then H3O plus will give us our ketone left back. And we should take note that this is a beta diketone, and it's a very useful intermediate because of those acidic protons between there. So how does that last step work? Let's see if we can do the mechanism for this. So first of all, I'm just going to come down here. We've got our double bond N, 6-membered ring, 5-membered ring. I'm going to go back to this one. And I'm going to have water that was present as part of our workup above. That's going to attack that carbon and push electrons up to the nitrogen. So that will give us water here. And what you should notice, each one of those steps is an equilibrium process. But this, what you should really notice, is that we're now returning the same way we started. So this is how we formed, this is the backward direction from how we formed that enamine or iminium salt. So I can transfer a proton internally, that's okay. We'll have a nitrogen with a plus charge on it now, and the OH here. I've got a good leaving group, so I'll just encourage that to leave, and I'll end up with double bond O with a plus charge on the oxygen, plus an N. I think it was just a 5-membered ring. We'll keep that. And then those electrons could always take the extra proton to return you to the keto form. So whether it has the allyl group on it or whether you choose to go back before you put it on, we'll just put that back in because that was the end of the first reaction we did. And so that allyl group is there.